All right. All right, so we're going to talk about line integrals on vector fields today. So last time we talked about the concept of a scalar line integral. Today we're going to use the idea of work to come up with our definition of a vector line integral. So first semester we said that work W is F dot PQ for force moving a particle along some path. And the idea is that only the force, the reason we do the dot product, only the force that is acting in the direction of motion actually produces work. What we want to do today is we're going to have a force F is some function of x, y, and z, and it's moving or acting on, I'll say that, a particle moving along some arbitrary curve. I'm in trouble spelling today. So we have a smooth curve C. So let's draw a picture here. So we have in our three-dimensional coordinate system, we have some curve C. So there's our curve C. And what we're going to do is divide C into several subintervals. So I'm going to call this our initial point, P0. This is our nth point, P sub n. And we're going to divide the curve into little intervals. And I'm going to draw a picture here. Here is the force acting at the ith subinterval. Ith. So this is F of x sub I, y sub I, z sub I. And I'm going to call this point P sub I. And at this, the distance here along the curve, that distance is going to be delta S sub I. And we're going to sum the work done in moving that. I'm going to move this P sub I to the other side of the curve so it's not. There we go. We're going to sum the work done as we're adding each little portion of the work as we move along the curve. So it's a familiar argument by now. So let me magnify this. So here is delta S sub I. Here is F sub I. And I'm going to draw another vector here. This is our unit tangent vector, T sub I. So T sub I is the unit tangent vector. Only the force that's acting in the direction of T sub I does work. at that point, at point I, at P sub I, at that point, only the force acting in the direction of T sub I does work. At P sub I, the unit tangent vector is in the direction of motion. So our small increment of work, I'm going to say delta W sub I, is equal to the force at that particular point, X sub I, Y sub I, Z sub I, dot T sub I. That's going to give us the component of the force, or the amount of the force, the magnitude of the force in the direction of motion, times delta S sub I. That's how far we move in that little interval. So we're going to sum this up and then take the limit as delta S sub I approaches 0, like we've done before. And this is going to be how we define a vector line integral. So we're going to sum, take the limit as delta S sub I approaches 0. And we get our definition of a vector line integral. So we get the work equals the integral over our curve of f dot t ds. Well, we know that the unit tangent vector, not difficult to calculate, but we have some relationships that we can take advantage of. So I'm going to say, recall that the unit tangent vector is r prime over the magnitude of r prime. And ds is the magnitude of r prime dt. So our work is going to be the line integral over our curve of f dot r prime. So if I substitute r prime over the magnitude of r prime for unit tangent vector, magnitude of r prime dot dt for our ds, I need one other thing, dt. And usually we write the integral over our curve of f dot dr. So this is going to be our definition of a vector or line integral on a vector field. So we're going to define this. Line integral of a vector field is the integral of f dot dr. And that is the same as the integral over our curve of f dot t ds. And I'm just going to write this out explicitly. This is the integral from a to b of our f. And we're going to have x of t, y of t, z of t, dot r of t dt, where f is a continuous vector field, and c, our curve, is given by r of t. That's our parametric representation for c. A less than or equal to t, less than or equal to b. So we have a parameterized curve. Yes? Oh, this should be r prime, yes. So we parameterize our curve using a vector value function. We represent our field in terms of the parameterization. So we get a representation of our field on the curve. And then we can evaluate this vector line integral. So the vector line integral tells us what we're doing is we're summing the tangential component of our field times the length we're traveling around this curve. So the vector line integral has something to do with the tangential component of our vector field. And what we're going to do, where we're going with this, is we're going to find a relationship between the tangential component of a vector field around a curve and the curl of the field in a region. So we're gonna make these relationships between these two things. That's part of the point of what we're doing in chapter 15 is to discover relationships between all these things. And what we end up doing at the very end is we have several generalizations of the fundamental theorem of calculus. So the way we can evaluate an integral over a interval by plugging in the values at the endpoints of our interval into some related function at the endpoints. So in Calc 1, the related function was the integral of our function. Here in vector calculus, the related function is a little more complicated. But we're going to talk about the integral of something over a region and having it related to something on the boundary of the region. And we'll do that in several different contexts. We'll come up with the last thing that we talk about, Stokes' theorem, is the most general statement of the fundamental theorem of calculus. So we get back to what we talked about, what you learned about in Calc 1. At the end of Calc 3, you have the most general statement of the fundamental theorem of calculus. All the other iterations of it comes from that one. All right. So let's take a look at how we're going to evaluate some of these, and then we're going to make a relationship, come up with a relationship between vector line integrals and scalar line integrals. Because to evaluate a vector line integral, we do a dot product, so we end up with a scalar that we're actually integrating. But we want to come up with a more explicit relationship between a vector line integral and a related scalar line integral. All right, so let's evaluate some of these. Questions before we go on? Okay. So the nice thing about this, when we first learn something like this, is the questions you get asked are just evaluate this. So we're just going to evaluate the line integral over our curve of f dot dr, where f is xy I hat plus yj hat, and our curve is given by, this one's already parameterized for us, for cosine t I hat plus 4 sine t j hat, for 0 less than or equal to t less than or equal to pi over 2. So what is our curve? And this tells us quarter circle. So we're going counterclockwise around a quarter circle with radius 2, 4. All right, so we want to represent f in terms of the parameterized curve. So on the parameterized curve, so I'm going to say on C, f equals 16 cosine t sine t xy I hat plus 4 sine t j hat. So on the curve, that's what our force is given by. R prime. Not a difficult derivative. What do we get? Minus 4 sine t I hat plus 4 cosine t j hat. So f dot r prime is going to be our integrand. Is, what do we get? Negative 64 cosine t sine squared t plus 16 sine t cosine t. And our line integral of f dot dr is the integral from 0 to pi over 2, now that we've done all of our work, of this quantity, minus 64 cosine t sine squared t. And this turns out not to be a bad integral. So that's our integrand. We integrate this, and it's not a difficult one. Be careful with your trig functions. They do have values when t equals 0. Minus 40 thirds. That's what this comes out to. So we can interpret this as the work done by this force on a particle moving around this quarter circle. So it does minus 40 thirds units of work as the particle moves around that. Depends on the units. Could be ergs, right?
Do we have
Dynes.
unit, just units, or just numbers,
Yeah.
no units?
Yeah, this is math, we don't care about units. Yeah. This is minus 4 thirds units of work. 40 thirds units, some unit of work. It would depend on what f is measured in and what units are.
We won't be required to iron out what units we
No, unless the problem specifically said a force of given by da 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 newtons and that moving around the path da 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 where meters. Yeah. All right, let's look at a three-dimensional vector field, a three-dimensional example. So we want to find f dot dr, where our force is x squared I hat plus y squared j hat plus z squared k hat. And our curve is given by, parameterized for us already, 2 sine t I hat plus 2 cosine t j hat plus 1/2 t squared k hat. And it's going to be 0 less than or equal to t less than or equal to pi. All right, what is this thing? What is this curve? A helix. And this, it's stretched, right? The loops are not evenly spaced. They become further and further apart. And how far are we going around it? Half a turn. So we could interpret this. You might be asked to find the work done by this force moving a particle around this helix a half a turn. All right. Well, you've seen that as we increase the number of dimensions, that we just end up increasing the number of, or the amount of work that a problem takes to do. Yeah, no pun intended. So force on our curve. Our force is 4 sine squared t plus 4, that's an I hat, plus 4 cosine squared t j hat plus 1/4 t to the 4th k hat. And r prime is 2 cosine t I hat minus 2 sine t j hat plus t k hat. F dot r prime. And the other thing that we've probably seen as we go through this is what used to be the problem, parameterize this curve, find the derivative of this vector valued function, now just becomes part of something that we do, find the dot product of these two things, becomes part of what we do for another problem. We get 8 sine squared t cosine t. And remember when we actually do these integrals, we get scalar quantities. (1/4 t to the 5th). So the integral of f dot dr. When I learned line integrals, we always said f dot ds. I don't know. 0 to pi of this quantity, 8 sine squared cosine t minus 8 cosine squared sine t plus 1/4 t to the 5th. And this is going to be dt. Not a difficult integral to evaluate. And this gives us pi to the 6th over 24 minus 16 thirds.
Oh my goodness.
Oh, because you can set that.
Oh, I forgot my t.
It's not the sine squared of
Cosine squared t.
Cosine squared of sine t. Oh, that would be ugly. Yeah.
Wow, thank you, Dylan, for your insight.
How about
All right, so this next one, I don't want to go through all of the steps. I just want us to remember one piece. All right, questions here. Okay. So for this one, we want to find the work. Done by f equals yz I hat plus xz j hat plus xy k hat. And it's moving a particle in a line from the point 0, 0, 0 to 5, 3, 2. So what do we need to do here? In the end, that's what we're going to do. But we need to find our work, we need to represent f in terms of our parameterized curve. So we need to parameterize the line. So we need to represent f in terms of our parametric representation of the line. Do you remember the parametric representation of a line?
No.
Yes.
R of t. That's not. That would just be a vector. We need to parameterize a curve so we can represent the force, because the force varies over the course of the line. R of t,
Vector times dot, thing where it starts.
x1, I'll say x0 plus at
Yeah, this thing.
I hat plus y0 plus bt j hat plus z0 plus ct k hat.
Yeah, I remember.
Where x0, y0, z0 is on the line.
Wait, wasn't there a part of this that had a plus d that was?
That you're thinking of the equation of a plane, I think. X0, y0, z0 is on the line, and the vector a, b, c is parallel to the line. So what vector is parallel to this line?
5, 3, 2.
5, 3, 2.
Just use that as our
And what point would be convenient to use for our initial point? 0, 0, 0. So we get R of t is 5t I hat plus 3t j hat plus 2t k hat.
basically just a normalized initial, but
What's T going from, Kevin?
And t goes from 0 less than or equal to t less than or equal to 1. So then on the line, f then becomes 6t squared I hat plus 10t squared j hat plus 15t squared k hat. And then we can proceed from here. So the reason that we have to parameterize that line, we can't just do f dot pq, is f varies from 0, 0, 0 to 5, 3, 2. So and this represents how it varies as we move along that line. I'm going to say proceed from here. So not a difficult integral to evaluate, but we had to remember how to parameterize a line.
so f dot pq only works if f is a constant force.
Yes.
That doesn't vary.
Well, we found work done by a variable force, but it was f was varying in magnitude in the direction that we were.
And that's f dot pq.
That's f dot pq, and we could integrate f dot pq, but f was varying in magnitude, or our amount of the mass was varying. The force was constant, or the mass was. So when we were pumping, the mass was varying as we. Right. But the force was acting in a single direction.
Same way. And this
Right.
is, of course, not all the same.
Right, right. The force is acting in various different directions at every different point. All right. So let's find a connection between vector line integrals and scalar line integrals. So that is what we call the differential form. So the differential form, and one reason that we're going to talk about the differential form is vector line integral expressed in differential form is going to be related. We're going to use that to make our relationships that I was talking about earlier with some other things. All right, so a quick recap. For a scalar line integral, we had the integral over our curve of f of xy ds. That's how we wrote a scalar line integral. And we interpreted this as multiplying some function times the length at each point along the curve. And we said we evaluate this by doing the integral from a to b. We express f in terms of our parameterized curve, f of r of t, times the magnitude of r prime dt, where our curve is represented by this vector valued function. For a vector line integral, we have a vector field f. I guess I could write here we have a scalar field f. Our vector line integral, the integral over our curve of f dot dr, is the integral over our curve of f of r of t. So we represent our force in terms of our parameterized curve. And I guess I should put this as a to b once we parameterize the curve. Integral from a to b of f of r of t dot r prime of t dt. So these are very similar. So we're gonna kind of make a relation. We're gonna talk about how we can represent this vector line integral as a sum of scalar line integrals. Then we see that when we do the dot product, it comes out that way. But we can represent it in a nice kind of compact way. All right, so we're going to use the notation that f is m I hat plus n j hat. If we had three dimensions, we would just have another component. And we're going to say our curve is given by a vector valued function, r of t, and I'm going to say that's x of t I hat plus y of t j hat. In this case, f dot dr, or f dot r prime is going to be dx dt I hat plus dy dt j hat. So f dot r prime is m dx dt plus n dy dt. When we do that dot product, and our line integral then becomes f dot dr is the integral over our curve of m dx dt plus n dy dt dt. And we can write this, these dt's cancel, and we can write that as the integral over our curve of m dx plus n dy. And this gives us our relationship between the vector line integral and this is a scalar line integral. So that's our relationship. We can write f dot dr when f is written as m I hat plus n j hat, and our parameterized curve x of t I hat y of t j hat as m dx plus n dy over our curve. And with three variables, we would say f is m I hat plus n j hat plus p k hat, and our vector line integral f dot dr is the integral over our curve of m dx plus n dy plus p dz. We call these two forms the differential form of the vector line integral. So our vector line integral can be written in differential form as a sum of scalar line integrals. And we will see this notation quite a bit moving forward.
So if you want, this would be extremely useful because it gets rid of the fact that you have to deal with the DT.
Right, this gets rid of the fact that we need to parameterize the curve.
So that's why you want this. So you would just take you just use dx and then
Dx and dy. We'll do a couple of examples using that. So I want to talk about some notes now. Some important things to remember about line integrals, and then we'll do some examples in differential form. The magnitude of a line integral is independent of the parameterization. We can parameterize our curve however we want. The magnitude of our line integral is not going to change. So the amount of work done or the mass of a curve, if we're talking about a scalar line integral, the mass of a wire, that's not going to change depending on how we describe the curve. The orientation of the curve so which direction we're traveling on the curve affects the sign of a vector line integral. So this would be in differential form mdx plus n dy plus p dz. Specifically, i.e., the integral, if we go the opposite direction of f dot dr, is the negative of the integral going in the positive direction. And the reason is that because t changes direction, our unit tangent vector, for an opposite orientation. The orientation does not affect a scalar line integral, because if we interpret it as the area of a fence below a surface, the area of the fence doesn't change sign depending on which way we go along the fence. It's just a positive area. The mass of the wire doesn't change if we add up the pieces going this way versus going this way. All right, so let's look at evaluating some line integrals in differential form. So any questions? Any questions here? All right. So we want to find f dot dr, where f is x squared y I hat plus x y to the 3/2 j hat. And our curve is given by r of t is t plus 1 I hat plus t squared j hat. 0 less than or equal to t less than or equal to 2. Well, I'm going to note that the integral of f dot dr, line integral f dot dr, is a line integral of m dx plus n dy. And here, m is x squared y, and n is x y to the 3 halves. On the curve, x equals t plus 1, dx is dt. And y equals t squared, and dy is 2t dt. This should be a dx, sorry. All right, now I can just substitute in these quantities. I'm going to evaluate the line integral this way. So our line integral over our curve of f dot dr is the integral from 0 to 2 of m x squared y, which is t plus 1 squared times t squared dt, because dx equals dt, plus n, which is t plus 1 y to the 3 halves. Well, y is t squared. T squared to the 3 halves is t to the 3rd. And then we have times dy, 2t dt. And this is an easy integral to evaluate. And that gets 256 thirds.
Yes.
So we didn't have to take r prime here. Well, we kind of did. This is kind of like doing r prime. Just finding our dx and our dy. But just a slightly different, different process.
So this might sometimes be less of an x if you have a particular.
Right. But let's do one more example. I want to do one more example to show when this differential form is especially useful. So let's evaluate the integral over our curve of 2x minus y dx plus x plus 3y dy, where a curve is the arc on y equals x to the 3 halves from 0, 0 to 4, 8. Now what we would do previously is this was not a difficult curve to parameterize, let x equal t. And then we could substitute. Now this is equivalent to saying that f is equal to 2x minus y I hat plus x plus 3y j hat. And this is the same as the integral of f dot dr on that curve, writing f like this. But since we have this nice curve, we can say that m, this is n. Well, what is dx? Isn't dx just equal to dx. Dx equals dx. dy is 3/2 x to the 1/2 dx.
Excellent. So now it's all in.
Right? And this is going to be from 0 less than or equal to x less than or equal to 4. So we replace all the y's with x to the 3/2, and we're just evaluating an integral in terms of x. So we have the integral from 0 to 4 of 2x minus x to the 3/2 dx plus x plus 3x to the 3/2 times 3/2 x to the 1/2 dx. That's dy. And this just becomes integral from 0 to 4 of 9/2 x squared plus 1/2 x to the 3/2 plus 2x dx. Nice, easy integral to evaluate. And we get 592/5. So we've bypassed the step of parameterizing our curve, finding our prime, representing f in terms of our prime. We kind of condensed that all together in this step here. And you would get the equivalent answer if you did the problem the way we've done before. Parameterize our curve, represent f in terms of the parameterization, and did the integral that way.
So this is especially useful if you can make everything one variable
Right.
very easily, because you have some sort of a direct relationship, like y equals some thing
Mm-hmm.
x,
Mm-hmm.
and that would be the one for us.
And we will see something special happen when we talk about line integrals of over conservative fields. And we will talk, the conservative fields definitely come back. Conservative fields are very nice. And we will also talk about what happens when we do a line integral around a closed path. And something really nice happens with line integrals of a conservative field around a closed path.
I'm just gonna write up every answer. Well, if I was a teacher, I'd make it like that. Like every answer is 12.
That'd be kind of cool, dude. So like, you didn't have to check it.
Yeah, but then kids would catch on.
Yeah, but it's about the.
I always thought it'd be good to make a multiple choice test. I told you that before, where every answer is like C, except for one.
I'd take
It
that
would be
all
even
day.
better is if you
Yeah,
made it
once
so
you
that
realize
there's
how,
one
like,
that was a
you're
normal multiple choice, one
Right.
version was a normal multiple choice test, and another version, every answer was C,
Second guessing yourself.
and distributed them randomly,
Oh yeah.
and watched everyone argue.
Or just a 2-question multiple choice test.
Mr. Shoot,
Not.
Mr. Shoot put like there's 12 A's, 4 B's, and like 3 C's and 6 D's.
Oh yeah, I've heard
Oh my
about
god,
that.
that annoyed me
That's
so
like
much.
just a
Yeah.
second.
And then remember for Christmas,